So there are different types of chemical bonds. We've mentioned them before. Why do chemical bonds even form? They form because they lower the potential energy between the charged particles in the atoms. So as two atoms approach each other, there's a very complicated set of interactions. We have repulsion between electrons because they are like charged, they're all negative, and so they repel each other. The nuclei are positively charged and they repel each other, but there's attraction between electrons and the nuclei. So all of these things come together and we have to look at the overall attraction. So a bond will form if those interactions combine together, give a net reduction in energy. It's more stable then, and a bond will form. So ionic bonds occur between metals and nonmetals. We've looked at trends on different properties. Metals have low ionization energies. It only takes a little bit of energy to remove an electron from a metal atom. So metals lose electrons fairly easily to form cations. Nonmetals have negative electron affinities, meaning that when you give them an electron, it actually releases energy. So they form anions. So we've got anions and cations, positive and negative charged particles, and they will attract each other and form an ionic bond. So between metals and nonmetals, we get ionic bonds, and the characteristic of this is that electrons are transferred from the metal to the nonmetal. The two other types of bonds that we need to know about are covalent and metallic. Covalent bonds occur between different nonmetal atoms. Nonmetals tend to gain electrons. They're not going to form ionic compounds with other nonmetals because none of them wants to become positive. They all want to become negative, and that's not going to do any good. So what they do is they share electrons instead of transferring them. And then metals also form bonds. There's got to be some sort of a bond, or metals would not be solids at room temperature. And we know that they are. In a metallic bond, the electrons are pooled, and we'll talk about that in a little bit. So in a covalent bond, electrons are shared. So here we have an illustration. We've got the positively charged nuclei, having pointer issues as always. The red dots there. Those are going to be repelled by each other, but they are surrounded by electrons. And so this electron is going to be attracted to this nucleus and to this nucleus. If that electron is between the two nuclei, that's going to be the lowest potential energy situation because it maximizes the attraction and minimizes the repulsions. So this will be the lowest potential energy. If the electron's over here, it's not going to have as much attraction with this nucleus, and so this will be a higher energy. So the most stable arrangement is when you have the shared electrons between the nuclei. And this is a covalent bond. Electrons between the two atoms being shared, and that negative electron or electrons hold the two nuclei together. Any questions? It's helpful to remember Coulomb's law, just in its very basic form, that the energy, the potential energy between charged particles is proportional to the charges on the particles and inversely proportional to the distance. So in this center one, the potential energy here is the most negative, the lowest, because we have oppositely charged particles. That's what makes it negative. Say +1 and -1, it's going to be a negative number. And the distance here is the smallest. Smaller distance, larger negative energy. This is going to be a higher energy, closer to 0, because the distance between the electron and the nucleus is larger, and so it's not as strong of an attraction. In metallic bonding, this happens between metals. We know that metals lose electrons fairly easily. That's why they form cations. But again, we can't get ionic compounds forming between two different metals because none of them want to be the anion. They all want to be cations. So the simplest model to understand metallic bonding is called the electron C model. And so the idea here is that we have metal atoms basically in a lattice pattern. So we can think of this as one metal atom, and here's another one, and here's another one. And they're going to arrange themselves in a particular pattern. And their valence electrons are not being transferred from one to the other. They're not being shared between two specific nuclei. They're just sort of free to roam about. And so what color should we use for those guys? Maybe orange. So each of these has let's say we've got something like sodium, and each of those atoms has a valence electron. Those valence electrons are very loosely held by the nuclei, and so in this situation of the pure metal, those electrons are free to move around. I think of this a lot. You know, I've told you that electrons remind me of my son Andrew, or of little boys in general. So I think of the nuclei as more of like the home, the family, right? So this is a lot like a neighborhood. Back in the days when children were allowed to roam free, it was a good thing. So all of these circles are the houses, and here is a little boy from each of the houses, and the mom sends them out to play in the morning. And they just run around the neighborhood together. And the children out there playing together sort of bond the neighborhood together, right? Because you know the other moms, because their kids are playing with your kids. And so these electrons are sort of swimming around. That's why we call it an electron C model. They're pooled, they're just moving, they're sort of fluid. But the attraction between all of these negative electrons and the positive nuclei is what holds the metal together. Does that make any sense? It's weird. And we'll learn later how that model explains some of the properties of metals.